In this final and third video of this video series on the photoelectric effect, we are going to focus very briefly on problems that involve photoelectric effect graphs. Now, in the simulation that I use to illustrate the photoelectric effect, we plotted graphs on the side that were kinetic energy versus frequency graphs. And the kinetic energy was a measure of the maximum kinetic energy of electrons leaving a metal surface when irradiated with photons of light or electromagnetic radiation of a high enough energy. And what we found is that initially, as the frequency of the incident radiation fell on the metal surface, there was no kinetic energy measurement because no electrons were leaving the surface. At the threshold frequency, the electrons that popped out on the surface would have no energy, but as soon as the frequency increased more than the threshold frequency, we would get electrons with kinetic energy greater than zero. And as the frequency increased, so the actual energy of the electrons hitting the anode on the other side of the photocell would increase. We also learned about Einstein's equation, and Einstein's equation is very simply conservation of energy, the energy of the photon, remember component 1 equals the work function, component 2, the minimum energy required in order for an electron to leave the surface of the metal. You can think of it as an energy toll that the electron has to pay in order to leave the surface. And then lastly, the kinetic energy of the electrons that leave the surface, and that's component 3. Applying Planck's equation for the energy of a photon and substituting Planck's constant times the frequency of the photon in place of the energy of the photon, we get this equation. Now, rearranging it in such a way that we take W0 to the left-hand side, we then make the kinetic energy, the maximum kinetic energy of the electrons measured, which appears on the y-axis or on the dependent variable axis. We make that the subject of this equation. And if we now use the fact that this is a straight line and write the general equation for a straight line in the form of y equals mx plus c, then we get to see some really interesting things that come out of this equation. So x is the frequency of the photons, that's along the x-axis, and y is the kinetic energy. But notice that the gradient is, in actual fact, Planck's constant. So if we look at the change in kinetic energy on this graph versus the change in frequency, which would give us the gradient, then in actual fact, it gives us Planck's constant. So Planck's constant, h, would then be the change in kinetic energy over the change in frequency between 2 points on this graph, there and there. The other thing we see is that the work function is equal to the y-intercept. But now, this graph doesn't have a y-intercept. It ends, or should we say it starts, at the x-intercept or the frequency intercept. But if one looks carefully, we'll see that the y-intercept is in actual fact equal to the negative of the work function. So if we now extrapolate this graph, by that we mean we extend it beyond the data set of what we have, and we extend it until we get to the y-intercept along the y-axis, then what we find here is that this y-intercept is equal to the negative of the work function. Now, looking here, you can see that here is 0, so this value, which is a imaginary value, and when by imaginary I don't mean it's an imaginary number in the context of square root of -1, I mean it's actually not a physical value that would be measured in the experiment, but rather extrapolated, we find that this is a negative value, but yet it's equal to negative work function. Well, that should make sense because the work function in actual fact is positive. So by having a negative value equaling the negative work function, so let's say the value was minus a, then the minus signs disappear, and so we get that the work function is in actual fact equal to a positive value, and it would be an energy. So now that we have a broader view of the mathematical interpretation of a kinetic energy versus frequency graph for the photoelectric effect, we can now move on to examination questions involving graphs. So in this examination question, we are presented with the following graph. And it states a learner is investigating the photoelectric effect for two different metals, silver and sodium, using light of different frequencies. The maximum kinetic energy of the emitted photons, or should I say photoelectrons, is plotted against the frequency of light for each of the metals, as shown in the graphs below. Define the threshold frequency. Which metal, sodium or silver, has the larger work function? Explain your answer. And name the physical constant represented by the slopes of the graphs. Now, the definition of the threshold frequency is, in essence, it's the minimum frequency that is required of incident electromagnetic radiation that falls on the surface of a metal to liberate electrons. We will get to the formal NSC definition soon enough. 10.1.2, which metal, sodium or silver, has the larger work function? Now, keep in mind that the work function is the minimum energy required for photons of electromagnetic radiation to emit electrons. So here we have the threshold frequencies for sodium and for silver, and keeping in mind that the work function of a metal is equal to Planck's constant times the threshold frequency, and we can see that this is a direct relationship. In other words, the bigger the threshold frequency, the bigger the work function. We can then see that sodium is going to have a lower work function than what silver is, because sodium has a lower threshold frequency than silver, and we will explain this in more detail, more formally, soon enough. And then name the physical constant represented by the slopes of the graphs. Well, we've already referred to the fact that slopes or gradients are with graphs of kinetic energy maximum versus frequency give us Planck's constant. So referring to the official NSC exam memorandum, we can see here that there are in actual fact two official definitions that are accepted in the NSC. And please keep in mind that the definitions are marked very strictly. So it's that part of the content that you really do need to learn very, very well. And one shouldn't just try and wing it, as it were, in an exam situation by putting down what you think the concept means. That would be fine if they asked you to explain the concept, but defining the concept is a bit like stating a law in a court of law. You've got to do it virtually word for word. So the threshold frequency is the minimum frequency of a photon needed to emit electrons from the surface of a metal or substance. So the words in the brackets can also be substituted there and it will be accepted. Or it's the frequency of a photon or light needed to emit electrons from the surface of a metal with zero kinetic energy. In other words, when that photon with minimum frequency, in other words, frequency equal to the threshold frequency, hits the surface, it's going to result in an electron right on the surface popping out of the surface and staying there because it has no net kinetic energy to move away from the cathode. Now recall we said that the silver has a higher work function. So one could answer this by saying that the threshold or the cutoff frequency of silver is higher, which we did. And because the work function is directly proportional to the threshold frequency, or the work function is equal to h times the threshold frequency, it's going to have a higher work function, which is what we said in essence. But it's really important that one puts it down formally on paper in such a way that you will receive the 3 marks. Another way of answering this is to say, to eject electrons with the same kinetic energy from each metal, light of a higher frequency or energy is required for silver. Since the energy of the photon equals the work function plus the maximum kinetic energy, and the kinetic energy is constant, the higher the frequency of the photon light required, the greater is the work function. Now, personally, I am not too keen on an answer like this. One, I think it's difficult to construct. Secondly, it's not always so easy to mark. I would strongly suggest that you try to answer questions like this using bullet format. The simpler, the better. It's a 3-mark question, so invariably there's a mark for the direct answer, and then there are 2 marks for explanation. 10.1.3 we've already answered, and the question was, what does the slope or the gradient of those 2 kinetic energy versus frequency graphs represent? And it's Planck's constant. In 10.4 it asks, if light of the same frequency is shone on each of the metals, in which metal will the ejected photoelectrons have a larger maximum kinetic energy? Now, if we look at the graphs, here is the kinetic energy axis. And remember, it's the maximum kinetic energy of the electrons that's measured on that axis. And here is the frequency axis. And the graphs for sodium and silver are parallel to each other. And silver has a higher threshold frequency. Then if we have a frequency of electromagnetic radiation that is shone on both metals, so let's say the same frequency of light is shone on both metals, let's call it frequency star, then we see that the kinetic energy of the electrons leaving the surface from the silver will be lower than the kinetic energy of the electrons leaving the sodium. And so the answer, and it is only for 1 mark, is sodium. It says, in which metal will the ejected photoelectrons have a larger maximum kinetic energy? And the answer is sodium. Now, it is only for 1 mark, but the conceptual understanding is quite deep, because we can see from interpreting the graph that the answer is sodium. But why? Well, quite simply put, the energy toll that an electron has to pay in a silver surface is higher than in a sodium surface. So if you have photons of the same energy hitting electrons in the 2 different surfaces, the electrons coming out of the silver surface need to have paid a higher energy toll, so they have less energy left over in the form of motional or kinetic energy. Whereas the sodium, the work function is less, so the electrons coming off have to pay less of an energy tax, as it were, so they have more left over, more kinetic energy left over than in the case of the silver. So if we look at it mathematically, we know that Einstein's equation says the energy of a photon is equal to the work function, or the energy toll, plus the kinetic energy of the electrons leaving the surface. So if we rearrange it and make the kinetic energy the subject of the equation, then we see that the energy of the photon, which would be constant in both cases, minus the work function, which varies, is going to equal the kinetic energy. So if the work function is larger, if that increases, then because the energy of the photon is the same, it means the kinetic energy is going to decrease. So this would be the case for silver. If we have that the work function decreases and it's smaller, as in the case of sodium, well then the kinetic energy of the electrons is going to be more. So there are different ways of answering this question conceptually, arising to the same answer. But don't be misled. This 1-mark question requires a deep understanding of the phenomenon. So in conclusion, let us summarize the concepts that we have covered in this video on graphs. We have focused on graphs for photoelectric effect where the maximum kinetic energy of the emitted electrons is plotted versus the frequency of the electromagnetic radiation incident on the metal surface. The graphs have a shape like this, which is a straight line, which has an x-intercept or a frequency intercept that is away from the origin. So first and foremost, this frequency intercept, we must remember, is the threshold frequency, sometimes also symbolized as F0 in certain textbooks. And that is where we can read off the minimum frequency required for photons to emit electrons off a particular metal surface. Now, one needs to be very careful when answering these questions, because you need to look here at in what unit and at what scale is the frequency measured in. So the threshold frequency for sodium, which is 5,94, is not 5,94 for sodium, but 5,94 times 10 to the 14 hertz. This 5,94 needs to be placed in front of times 10 to the 14 hertz. So please remember, when asked for the threshold frequency, you need to combine this number and that power of 10 in front of the hertz. You will also need that if you're going to do further calculations. If asked to use the graph to determine Planck's constant, then one needs to work out the gradient between 2 points on that graph. So that would be rise, which is the change in kinetic energy, over the run, which is the change in frequency. So Planck's constant would equal the gradient, which in mathematics we refer to as m. Don't get that mixed up with the m for mass. And that would be change in y over change in x. And in the context of this graph, the change in y, or the change in the dependent variable, is the change in kinetic energy. And the change in the independent variable is the change in frequency. And this would give us Planck's constant. Then if we were asked to use the graph in order to determine the work function, we would need to extrapolate. We would need to expand the graph beyond the data set that is presented here. And that would mean we would have to draw a line to the y-axis, or the kinetic energy axis, and there the y-intercept c is in actual fact the negative value of the work function. So there we would need to, let's assume that this was minus 3, and here too you need to be careful because we're dealing with such small values. They very often put a power in with the unit when they label the axes for these graphs. So this would be minus 3 times 10 to the minus 19 joules. And so the work function would therefore be 3 times 10 to the minus 19 joules, because the minus signs would cancel out. So this is really very important, because every now and then you will encounter graphing questions like this in the questions from past examination papers. So this is really very, very important to practice and to understand these types of problems. And together with the calculation problems that we have already covered, if you do enough of this sort of practice in past examinations, you should be more than prepared for what you encounter in your control test and what you're going to encounter in your June exams, your prelim exams, and your final exams. So I hope that this series of videos has helped you to gain a deeper understanding of what is truly a remarkable discovery in the early 20th century in explaining not only the photoelectric effect, but the duality of light. And by that I mean the wave nature and the particle nature of light, which defies common sense, but in actual fact is a reality that all scientists fundamentally struggle with.